So hello everyone, this is lecture 22 for the mathematical physics, and in the last lecture we just completed the matrices, and from today onwards we will start the ordinary differential equations, or can say linearly ordinary differential equations. We will understand the differences. Okay, so in it we will study the first and second order differential equations with degree 1. Okay, so you will know what is degree and order. So let's just see first the syllabus. Okay, what we will study in this whole differential equation thing. Okay, there will be 8 to 9 lectures for this. So first we will see the introduction of different terms which we will use in whole syllabus. Then we will see the first order differential equation. In that we will see the how to find the solution of first order differential equation using separable differential equations. Then we will study about the homogeneous equations and how to reduce that equation to separable form. Then equations reducible to homogeneous form and homogeneous to separable. That's how. Then we will see what are exact differential equations. Then equations reducible to exact form, linear differential equations reducible to linear form. So all are related to each other. Okay, so we will study all in that section. Then we will study the second order differential equation. In it will be homogeneous equations with constant coefficients, Euler's-Cauchy form of homogeneous equations, and this is the form of Euler-Cauchy. X square y double dash ax y dash by equal to 0. Here dash represent the derivative, means double dash will be second order and single dash will be single order. Then we will see the concept of Wronskian. In it we will see the linear independence of solutions. Then non-homogeneous equations with constant coefficients. Then again the Euler's-Cauchy form in some advanced stage we will see, that is x square y double dash ax y dash plus by dash equal to xm. Okay, x to the power m. So this will be our syllabus for the differential equation. So let's start. First, what is a differential equation? A differential equation is an equation containing derivatives of various orders with respect to one or more independent variables. So what are variables and independent? So if we have this kind of equation of a function, you know this, you are very familiar with it. So here this x is nothing but it is independent variable, and this fx, which is y, is dependent variable on this x. When there is only one independent variable in the equation, then we call that equation as ordinary derivative. Okay, means there will be capital D or small d here, d is y by dx, d square y by dx square, because it is a complete derivative. So that's why, because of only one independent variable, so we write it dy by dx, d square y by dx square, and this third order. Okay, and the example of this ordinary differential equations are like this: dy upon dx plus xy e to the power x. So here only one independent variable you can see, and second one is y, that is dependent. Okay, so there is one more example like this. It is also example of ordinary differential equation. Then we will see the second kind, that is PDE, partial differential equations. So here let's say psi is the function, and this equal to this psi is a function of x and y. This is f of x and y. Now we have two independent variables on which psi depends. So we call this, now we will have the derivative partially, means when we derivate with respect to x, then we take y constant. When we derivate with respect to y, we take x constant. So that's how we can write the partial derivatives: del psi by del x, here y is constant, and del psi by del y, here x is constant. And these are the examples of partial derivatives, all kinds of forms. And when the equation involves this type of derivatives, then we call that equation as partial differential equation. Like you know the wave equation, this is del square psi by dx square equal to 1 upon v square del square x by del t square. So this is an example of partial differential equation. And you also study about this heat equation. This is also an example of partial differential equation, because here are two variables you can see. If there is only single variable, then you don't need to put del here, it will be just d. Okay, so that's how you can differentiate d and delta, means del. And one more example is Laplace equation for the partial differential equation, you can see. Okay, now I hope it is clear to you, the differences and this introduction of differential equations. Now let's see what are order and degree of differential equations. You studied about this in the 10+2, but let me remind you again. The order of differential equation is the order of highest derivative of differential equation. So inside a differential equation, the highest derivative term, the power of that will be called degree, and that highest order will be the order of the whole differential equation. Means let's see one example, it will be clear to you. The degree of differential equation is the degree of highest derivative when differential coefficients are made free from radicals and fractions. What are radicals and fractions? These are like under root, any differential equation in the under root or the fractional power. So it should not be in this form, so that should be removed. After that only we can determine the degree and the order. So like we have this example, dy by dx whole cube minus d square y by dx square minus 2 equal to 0. So here you can see the highest order derivative is this, second order, and the power of this is 1, so that's why order is 2 and degree is 1. Here we will see that highest order is this and the power of this is 1, so order 2, degree 1. Now there is one more kind of example like this. Here it has 1 by 2 power, so it is a radical. Okay, so and the power is in fraction, so we need to solve it first. Like we take these both of 2 in the right hand side, then we will square this, then we will get this kind of equation, d square y by d square this. Here now the highest order is this and the power of this is 1, so order will be 2 and degree will be 1. Now one more example, let's see. This third 2 means it has the power 1 upon 2, it has power 1 upon 3. This is third. Okay, so you will have this kind of equation, 1 upon 2 and 1 upon 3. Just cube both sides, then we will get 3 by 2 here and just simple this term here. Now if we again square these both terms, then we will get 3 here and 2 here. So now it is free from radicals. Now we can see highest order is this 3 and power of this is 2, so order will be 3 and degree will be 2. So that's how sometimes you need to solve the equations to get the order and the degree. Okay, now we understand what are ordinary differential equations. Now we see that what are linear ordinary differential equations. So an ODE is said to be linear if power of dependent variable and their derivative equal to 1. Means the powers of dependent variable, that is y, should be always 1 and its derivative should also be 1. Okay, it means this kind of things are coming in the equations, then they should have 1 power always. This whole term should have 1 power, this should all have 1 power, only then we can call it linear. And there should be no term in the ordinary differential equation containing the product of the dependent variables and the derivative of product of two derivatives of different orders or both. Means you can't have this type of condition here. Means the product of the two dependent variables, their derivative and itself, and second order derivative or first order derivative, means this type of terms can't exist inside the differential equations. Only then we can call it linear. Okay, if you are getting this kind of terms, then it won't be linear. So these can't exist. Now the example of we can see, this is first order linear ordinary differential equation. How? Because it has no power, it is 1, the power of y is also 1, so we call it as, and it is first order, obviously this is the maximum order, and this is second order and power is 1, it has power 1, it has power 1, so it will be also linear ordinary differential with order 2. Now this has square, now it is not 1, so it is this y is coming in the sine term, so we will call it non-linear because it has power 2. Okay, it should be 1 for to be linear. Here also this term has power 2, so it will be non-linear ordinary differential equation. It will be differential equation but non-linear. Now when you understand the different terms, let's see an example how to find the solution of differential equations. So this kind of equations are called the differential equations, in which you are getting the derivative term, the dependent variable itself, and the independent variable. So when you have equation involving all of them, then that equation is called the differential equations. And this y dash is nothing but it will be a function of x and y. Okay, that's how you get the equation. Now you have to solve this kind of equation. How you can solve? So solution of equation 1 in some open interval a to b, when x is independent, so it can be in any range, so it should be in a to b, is a function y hx. So solution to which we will call the solution when we get something like this, y equal to hx, means y will be the function of some x, so that will call the solution of this equation. That has derivative y dash should be equal to h dash x, and derivative of y dash should be equal to h dash x, and that satisfy equation 1, and this should satisfy this equation 1 for all x in that interval. Okay, so then only we can call this y as the solution of this equation. And when there were some initial conditions were given, means when you solve these type of equations, you will get some constant because of this derivative term. When you integrate, you will get some constant terms, and to find that value of that constant term, you need to put these initial conditions. They will be given, only then you can find the solution, complete solution. Otherwise you have to write the solution in terms of constant. So first order ordinary differential equation, first method is separable form. Okay, so if the equation is given something like this, means it is a function of some function of y is given dy, and some function of x is given in dx. So just to make them in this form, means take the y terms up to dy with dy and x terms with the dx, then just integrate and you will get the solution. And in the last, put the initial condition x not equal to k naught, you will get the value of constant also. So let's see one example. 9y dash plus 4x equal to 0. So this 4x will be in the right hand side. This is dy upon dx, so dx will go with the 4x and dy is here. Now you know the integration, y square by 2 x square by 2, and you have this equation. Now it is came here, this side, here is this c dash. When you multiply with 1 upon 18 to whole equation, you will get this kind of equation, and this is the equation of ellipse. So this equation is the family of ellipse, because different constants you will get different type of ellipse. That's why we call this equation as family ellipse. Let's take one more example. Y square plus y dy plus x y square plus x dx. So how to solve? Just take the y common, x square plus 1 dy plus x y square plus 1 dx. Now just separate the variables, take the y terms with dy and the x term with the x. You will get something like this. If you just multiply and divide with 2, then 2y upon 1 plus y square, this will integrate to log 1 plus y square. How? When you try to differentiate it, you will get 1 upon 1 plus y square, then 2y. So this will be the integration of this. So you will get after solving this, and here you will get this, and some constant c dash. Now take this to this side and take 1 by 2 common, and log a plus log b is log ab. So this will be like this, and power 1 by 2 equal to it will be c dash, and then square of c dash equal to, we call it c. Okay, so this will be our solution for that differential equation. Now let's take one more example. Y dash equal to minus y upon x with y1 initial condition is given this time. So dy upon dx equal to minus y upon x. Just separate the variables, take the y with it, dy, x with this. So it will be log y log x plus c dash. You can take it also log c, then value will be different. If you take just c dash, then value will be different, and equation will remain same, the solution will remain same. That's definitely. If it is came this side, then log a plus log b log ab equal to c dash. It will be, just write it c, because of minus c dash it came. Then you know this should be c, and condition was given at x equal to 1 y equal to 1, means log 1 equal to c, and this is possible only when c equal to 0. Okay, because log 1 equal to c, then here it is e to the power c should be this and c should be 0. That's how we get c equal to 0. So substitute here and you will get this. This will be your equation. You have the values. Now one more example, x dy upon dx plus cot y equal to 0. Given initial condition at x equal to root 2, we have y equal to pi by 4. So just separate the variable first. It is minus cot y this side, then dx upon x and minus cot y will come in this side. So this kind of equation we will get. It will be tan y dy 1 upon x dx. Take the minus this side, then tan y dy is nothing but log sec y, and it will be minus log x plus log c. We take some constant. So always try to take constant in log now with when you are having log in the whole equation. Okay, that will be easy to solve. So now let's use the initial condition here. At x equal to root 2, we have y equal to pi by 4. So sec pi by 4 is again root 2. So we get this kind of equation, and when it came this side, then it will be 2 log root 2 equal to log c. It will be came inside and it will be square. So log 2 equal to log c, so c equal to 2. So we get the value of c, that will be 2. So this will be our solution. You can write it more like log x minus y is log x upon y. So 2 upon x. Just compare sec y equal to 2 upon x, and x will be 2 cos y. Now this question is asked in the previous year in the NET exam. Let's see. This is very easy. The solution of the differential equation with initial condition, this is dx by dt equal to x square. Initial condition is x at t equal to 0 is 1. Will blow up as t tends to. So we need to find at what t this equation will blow up. So the meaning of blow up is means the function so tends to infinity. So let's see. First find the solution. Take the x square this side and dt this side. Separate the variable. Then this will be minus 1 upon x, and here it will be t plus some constant c. Use the initial condition at t equal to 0, x is 1. So you will get c equal to minus 1. The substitute here t minus 1. Then x will be 1 upon 1 minus t. You will get this, and now you can see at t tends to 1, this will tends to infinity. So answer will be 1. Sometimes you have to use these options to find the values. Okay, just try to put them in the equation and see where it will go. So 1 will be the answer. So let's end here today's session. In the next lecture we will see some more examples, then we will go to the homogeneous equations. Okay, thank you everyone.